Hello, 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 and a warm welcome back to our beloved listeners here on the Science Show with Dr. Dada on JAMBO Radio Scotland, broadcasting from the city of Glasgow. Today's episode is a bit of a treat. It's a special episode we have today because we'll be veering slightly off our usual path into a fascinating peek behind the quantum curtain, if you like. We're going to be peering into the world of quantum tech. We will enjoy a talk from Samuel Horsh, a brilliant young mind from the world of quantum computing startups. Now, Samuel is going to share insights from his incredible journey at Quandela, where they are pioneering the use of photonic or linear optic quantum computing. And of course, in a world where quantum might just seem to be the latest buzzword, Samuel breaks it down. He brings it down to earth and shows us the real world potential of quantum technologies. The title of our show today is rightly From Quanta to Careers, Let's Talk About Quantum Computing. And that's kind of borrowing from the title of Samuel's talk, which is Let's Talk About Quantum Computing. Well, Samuel in his talk will cover two exciting angles. The first will be a glimpse into Quandela and the groundbreaking work that they're doing there. And of course, he'll also touch on career opportunities for the eager minds looking to dive into this quantum leap, if you like. And then there'll be a slight deep dive into the science behind photonic or linear optic quantum computing. And this will be kind of pitched at the level of undergraduates. So this helps offer them a window into the future of tech careers in this niche, in this area. So we'll also learn a lot from Samuel about his own experiences as a recent graduate from the University of Glasgow, now navigating the quantum technology space. And of course, before I forget, remember to keep the dial locked on DAB, on JAMBO Radio, and for the full color experience, head over to jamboradio.co.uk or to our YouTube channel to watch and listen live. Good. So, without further ado, let us dive right in. We have Samuel Horsh from Quandela, based in France. And yeah, we're really excited to see what he's going to share with us today. Over to you, Samuel.
Thank you very much. Yeah, very excited to be here. I was in your shoes 2 years ago, and I thought it would be just interesting to share a bit of my experience working at Quandela, where I started recently. So just quick about myself. So as I said, I did my master's here in Glasgow. I did math and physics, and I also did the quantum information course, and that was basically all I knew about quantum computing. And then I took a year out, and then I just applied for some jobs and found Quandela, and now I've been there for 5 months, and it's quite cool. I quite enjoy it, and I'll tell you a little bit what I've learned so far. And my aim is kind of to give you a bit of a insight of what's out there, but I'm not going to go into extreme details because that we don't have time for. And if you want to know more afterwards, feel free to message me or approach me. So the way I think about quantum computing, if now people ask me all the time, what is a quantum computer? So I came up with this runner's analogy. Thinking if you imagine two runners, one is a classical computer, one a quantum computer. I kind of think about the quantum computer having wings, and so just having extra abilities, because a classic computer just has bits, zeros and ones, and then can do loads of combinations of that. And a quantum computer just has some extra bits, superpositions of these so-called then qubits, and quantum entanglement, which a classic computer just can't use. So that's my idea. And if we now think about a racetrack, and the racetrack will be representing some kind of problem a computer might want to solve. And on most normal racetracks, actually classic computers are much, much better and much, much faster. So like if you want to just multiply two matrices together, you would not use a quantum computer for that, and probably will not for a very, very long time, because we've been using classic computers for so long. Therefore, we've optimized them to a very high degree. And so it's not that quantum computers will replace classic computers completely, but there will be some racetracks where actually a quantum computer might have an advantage. So in my analogy, it would be like if there's some canyon or some obstacle in the way, the quantum computer can just fly over it and take a shortcut, whereas the classical computer has to go a long way around or might not even be able to get there at all. So one of the best examples, I guess, you might heard of is Shor's algorithm, which is the factoring of big numbers into their prime factors. And that's something a classical computer struggled with a lot. And in theory, a quantum computer would be able to do that much, much faster. So that would be a case where we use our wings. But that's something which right now we cannot implement. And so if we look at kind of the current state of quantum computing there, it kind of falls into two categories. One is called NISQ, or Noisy Intermediate Scale Quantum Computing. That's a new term I learned as well. It was John Preskill came up with it. And that basically kind of describes a smaller scale quantum computer which might be in reach today or in the near future, which is limited but still can do some quantum computations, but it's not something which, for example, would be able to run Shor's algorithm. And then the full tolerant quantum computing era is kind of the thing we all think of if we think of like our quantum computers go and change the world, because that's where we have the scalability of going as large as we want, and we have error correction, which allows us to deal with any faults in the hardware, but to an extent where it kind of helps us in total to scale up more and more and more. So that's the ultimate aim, but that's, I would say, I mean, depending who you ask, but like 10, 20, 30 years away. And then the NISQ era is what we have right now, but so far there's no real applications or use cases which are actually useful. And that is kind of like finding these applications could be 1, 2, 3 years away, or could be not possible at all. Maybe there are no applications in that era and they're only in there. We don't know, but that's something which at the moment is talked about a lot, and that's kind of the two things. And then if we think about the actual quantum computers which we have today or in the future, we have to separate between hardware and software. So the hardware is really in the labs building the quantum computers, and there we have a lot of limitations right now. That's why we have this like NISQ era of having like noisy computation devices which really we don't know, we can't do that much about. And that will progress, and we get better and better in controlling these quantum systems. And there, I will show you in a second, there's loads of different technologies. It's not just one way of building a quantum computer. They're all completely different. And that's something which will progress, and we'll see how long it will take. And at some point, that will allow us to go into the full tolerant era. But that just like, we are not there yet. And then on the software side, we actually need to come up with algorithms and use cases what to do with the quantum computer. Because even though I mentioned Shor's algorithm, there's maybe a few more. Like there's something called Grover's algorithm, which is a bit like a sorting algorithm. But there's not that much actually out there, even for the full tolerant case, where we can do what we could do with a quantum computer yet. There is a lot of toy problems or proves that there is some advantage. So that we definitely know quantum computers have wings, but we just don't know if there's any interesting problems or where these interesting problems land in the kind of racetrack space. So, and then the same goes for the kind of like NISQ, like immediate, like today's problems, which we might be able to solve with the smaller scale quantum computers. And so a lot of work now is being doing, and that's what I'm doing, is to find some use cases and think about, okay, is there anything where we could have a quantum advantage and it is useful in industry or for anything which we actually want to do? Because there's a lot of examples where we have an advantage, but well, it's pretty useless. So we kind of merging that together is kind of the challenge. And both of these hardware and software parts, they have to progress in order to have like this big revolution, which people like talk about and why there's such a big hype around it. So just to see a little bit what's out there. So I copied this image. Don't be overwhelmed with all the fonts, with all the logos. So these are different hardware providers or different hardware technologies. So as I said, there's not one way of building a quantum computer. You can do it with atoms, either with ions or with cold atoms. You can do with superconducting computing. Then there's some like variations of that. The most common one or most popular one is superconducting directly, which is because IBM is doing it and Google and Amazon, so that's why it's the most popular one, because there's the most money in there. And then there is photons, and that's what we're doing. So that's slightly different to how the hardware works, and I'll explain a bit more in a second. But you can see there's a lot of different, here we have companies, and then down here we have some university labs we're doing it, and that's probably not an exhaustive list. There might be many, many more, and it will grow. But just so you have an overview, there is quite a lot happening, which I was quite surprised when I started working in the field. And now I've been to a few conferences, and it's very interesting. There's like it's, even though it looks maybe quite large, it's still quite a small community, and it's very fresh and new, and most of these companies are quite small. So yes, I mean, except of maybe IBM and Google, but even their quantum divisions are not like been there forever. So it's quite nice, I think, now to get into that field, because you're still like at the start and like can shape it with it. Right, and now I'll show you just a quick example. This is how our quantum computer in Quandela looks like, the one we have right now in our labs in Paris. And actually you can use it via our cloud for free, so you can try it if you want. We'll update it soon, but still it will be the same principle. So this is a NISQ quantum computer. NISQ, again, is this like noisy intermediate scale quantum computing, which is not really gonna bring massive advances, but there might be some application we can do with it, and then it's just like a stepping stone to get to that fault tolerant era. And the way this one works is we have a single photon source. This is a quantum dot. I'm not going to go into too much detail exactly how that works, but basically we have a single photon source, and that's really important, because we use then these single photons and send them into an interferometer. So just pure linear optics. We have some beam splitters and some phase shifters. So just some basic, just like an interferometer where we can send, in this case, 6 photons at the same time into this interferometer. And then we have actually in there 12 modes where we could send them in. It's not just 6 input modes, but 6 photons in the same time. And then all the computation happens there, because you can represent that as some kind of unitary transformation of that state of photons which you send in, and then you get some output state. You measure in which mode you found a photon, and then by designing these unitaries in a particular way and doing many of these measurements, you can then solve some problems. So for example, a big thing what we're doing right now is something called variational algorithms, and that's kind of a field of quantum machine learning, because that's something which, well, is possible with these devices, and so that's why we're doing it. And there, basically what you do is it's a hybrid between quantum computing and classical computing. You basically start off with some random parameterized unitary matrix here, do some measurements, then send your results to the classical computer, do some classical optimization, update the parameters, so change maybe some phase shifters, some angles, do it again, and then go in loops until you find like the optimal setup, and then you get some results for your computation. One example for that is you can calculate the ground state of some molecules, or you could just do like some optimization problem for like anything basically. But right now we basically need to find specific combinations of quantum computing and classical computing to actually get an advantage, because in a lot of fields, or like a lot of parts of algorithms, a classical computer is much better. So it's kind of this like finding this little point somewhere in the bigger infrastructure where the quantum computer can give us an advantage, at least this kind of quantum computer. And it's all, I can use that, or you can use that using Percival, which is just a Python library designed by us for operating this kind of quantum computer, and it's all open source. So if you want to try it out, please do. I can send you some extra information if you want. And then you can use actually, either you simulate it on your laptop, or you can, well, send it to the cloud and then run it on the actual quantum computer. So yeah, that's just one example of how a quantum computer could look like. And there are many other ones which, well, will be very, very different. And then maybe just a little bit about my company. So we were founded 6 years ago. First out of a research lab, just building single photon sources, these quantum dots. And at some point they decided, let's build a whole quantum computer. And then they grew a bit more. And now they just got, again, a second round of 50 million euros funding. And so now we're growing a lot and they're hiring all the time. I only started 5 months ago, but there's already so many new people. I don't know all of them. And there's a lot of different parts in the company. So I don't know if you're all interested in theoretical work or practical work, but since we have our labs where we actually build the devices, there's a lot of practical experimental physicists working there. And then also we have a theory team and software team and applications team where we kind of like look more on the computing theoretical side, what we can do with that technology. And so if you do want a job at some point, you can have a look at our positions. There will be loads in the next months and years. And we also do a lot of internships. So if you're interested in that, that's something we do every year. And then another thing we do every year is a hackathon in Paris, where basically it's just like a weekend. We do some challenges. You all learn how to code on our quantum computer. And then there will be some prizes, and it's just an opportunity to do that. There's also a possibility to get that transport and accommodation funded, but that's like you have to like apply for the extra, and to signing up for the hackathon, you just have to sign up. And I don't know the date for the next one, but the last one was in November, so I guess after summer at some point there will be another hackathon. And if you just keep an eye on our LinkedIn or on our website, should be information about that. So that's maybe a first quick overview. So that's the start. Thank you.
Very good. So we'll take a pause there. We've been enjoying that insightful talk from Samuel Horsh, who's in Quandela, based in France. So Quandela, as we've been mentioning, is a quantum tech startup. And Samuel's story is very inspiring because he actually did his undergraduate studies in Glasgow, so at the University of Glasgow. And Samuel, through this talk, has been giving us an insider's view of Quandela, not just as a company, but as a beacon leading the charge in quantum computing. And of course, this is also accessible to the public via their cloud platform. Well, welcome back. You're still tuned into the Science Show with Dr. Dada on JAMBO Radio Scotland, broadcasting from the city of Glasgow. So we've been listening to a talk by Samuel Horsh, and he'll be going deeper into some of the technical details of how their quantum computing platform at Quandela, how that works. For those of you who are watching on YouTube, of course, you'll get to see his slides as well. So I encourage you to catch up. If you'd like to see more of the details, to go to our YouTube channel to watch that. All right. But before we proceed, again, a hearty thank you to IOP Scotland, University of Glasgow, for supporting this show and for helping us through this journey. Now, let's get back right into Samuel's talk.
So the individual components is, if you think of two modes of these, so one of the lines is a mode, or like optical fiber, you would have a phase shifter, which is acting on one mode, just changing the phase of the photon. Then you would have one beam splitter, and then another phase shifter, and that together is like one building block. And then you have just many of them next to it in like loads and loads of rows, and that then gives you that universal interferometer, which there's a scheme which allows you to then approximate any kind of unitary to some degree of error. Yeah. So the hardware is pretty boring or like unspectacular, but it's crazy that you can do quite a lot of different things with it. And you can, so I'm sure you've all heard about qubits, and that's kind of the way to think about quantum computing. There is a way of doing that there as well, but it's not the only way, because you can just directly just think about sending photons in, letting photons coming out. So it's more the state would be like in which optical fiber there is a photon. And then you have a bit more opportunities, but there's also a way to think about it as qubits. If you just say, okay, if the photon is, let's say in this one, it's qubit in state 0. If the photon is in the other mode, it's state 1. So that would be one way of encoding qubits, but there's always, you can basically do whatever you want. There's no one rule to do it. Yeah. So the way you think about it, if you just think about the qubit picture, like that's then general for all quantum computers, is you have, again, qubits, which also you have the state 0 and 1, and if you measure, you only get 0 and 1, but then you have all the superpositions of these two states. So you can think of a sphere called the Bloch sphere, and on the surface of this sphere, at the North Pole and South Pole, you have the state 0 and 1, and the classical computer just has these, and then quantum computer has all the other points on the sphere, which are superpositions of these two initial states, and that then gives you basically an infinite amount of different states in between, and each of these superposition states, if you measure them, will have some probability of getting 0 or 1. So if you measure, you only get 0 and 1. So the idea is then you start off with some quantum state, or you prepare some quantum state where you have some probability amplitudes of some combination, and then you encode your problem in some way that when you measure it, this solution to your problem is the most likely output. So let's say you have 3 qubits, so you would have 2 to the 3, 8 different possibilities of getting out. You could get 0, 0, 0, 1, 1, 1, 1, 0, so on. And one of them will be the answer to your question. And so you need to, in that bit, or in whatever other quantum computer, you have to change the quantum state in a way, without measuring it, that the probabilities change so that the answer to your output will have the highest probability, ideally 100%, but it's also okay if it's like, let's say 50%, and all the other ones are much lower, because then you can just do many, many measurements and get this probability distribution, and then you still get the right answer. So that's, so I guess the degrees of freedom is kind of, you can think about it in this way, and so there's definitely more degrees of freedom in a quantum computer than in a classical one. Yeah. This one has 6 photons and 12 optical modes where the photons can go in. So you see that 12 coming out here and only 6 going in, but they are actually inside. There's 12 in total. So you can decide where you can actually only put them in 6, but if you program with it, you can basically just decide where you put them in, and then it automatically makes it that they will always go in the same one. So it's so actually we're going to update this soon, and then we have, I think, 10. But it's basically just difficult to build. The more photons, the harder it is. The problem with photons is that they get lost on the way sometimes, and of course, if they get lost, then you can't do anything with them. So what happens is, you have the source, the photons come out of it with some probability, which is actually quite high for that, and that's why we're using this quantum dot source, so that's great. But then the longer it takes, and the more things we do with it on the way, the more likely it is that the photon will disappear, just getting absorbed from the environment. And they're coming out one by one, so we have to demultiplex them so that they're not temporal separated, but spatial separated, and then we can send them in at the same time. So getting 6 of them at the same time, the probability is already quite low that we managed that none of the 6 got lost on the way. And if you add more and more photons, it gets much, much more difficult. And so the ideal case, of course, is to increase that, and that is the plan. And it's, I think, the material of the chip, so of the photon chip, is silicon nitride, if I'm correct. Yeah, I think so. And then the other ones, these are optical fibers, and then they're just like mirrors and loads of other things. So yeah, that's basically what the people in our labs do to kind of come up with a bit better designs of this whole system, so that we reduce photon loss. Because, well, yeah, that's the main challenge in using photons, because they are the main challenge in other technologies is that the coherence time, which means the time as quantum state is stable and it doesn't change, that is quite short. So if you would have, let's say, a spin, like an electron in a spin state and in a superposition of two spin states, it won't stay that way forever, and it will at some point just like move into one of them, and then you lose the quantumness, and then you can't do anything with it. And in photonic quantum computing here, we don't have that problem because the photons are just there. The superposition is kind of by the spatial divide of the photons, so we don't have this like coherence time problem, but we have the problem that sometimes the photons just get lost. And one way to fix that is exactly what you said, using the right materials, the right designs. And then there's also a way of maybe trying to mitigate these, like even if there's some errors, to still get some information out of it. So there's also the theoretical side on that. Yeah. Yeah.
So I have a question. So what's a day in your life like? What's it like working, like doing your job?
Yeah.
Share that with us.
It's not very like set. It's quite open. It feels a bit like research or kind of university, but not having exams and getting paid. So it's quite nice. And so I read a lot of research papers if I start some project or if I just need to know something, sometimes really specific to some algorithm or some hardware. And sometimes I just Google on Wikipedia how you do some matrix calculations or something which I forgot, or just read up on some concepts because it's always kind of a lot of things which I learned at some point maybe at uni come up again and again, but of course I didn't remember all of them perfectly, so I need to like relearn them. And then since I'm developing algorithms, I'm programming a lot, so I'm learning a lot of Python programming and our library Percival. And it's quite cool because we have a software team and I can just ask them all the questions and they really know what they're doing. So that is really cool. So it's a lot of learning, exploring new avenues, and then every now and then you have some meetings, but it's quite chill in terms of that. And it's a lot of you do you and find something out. And that's I really like in my team, especially, is that people don't really tell me what to do, and I can really decide myself what I think is a good idea to work on. Yeah. Yeah.
Very nice. Would you also like to share with us the algorithms that you've been able to, that one can run on this chip, for example?
Yes.
What kinds of examples can you mention?
Yeah, so one thing I guess I mentioned was this variational quantum algorithms. That's a group of algorithms which can be run on this one, but also on other devices. And there there's a few different things what you can do with it. So one what I mentioned was the variational quantum eigensolver is to find the ground state energy of some atoms or some molecules. And then there's a lot of other machine learning algorithms. So for example, we had last week we went to a hackathon at MIT where we had a challenge for them, which was designing a generative adversarial neural network, but in a quantum way. So it's basically a circuit or like a algorithm which generates something new, ideally maybe like a picture or something. For now, it will be something a bit more simple, and that could be either using quantum data generating quantum data, or it could be using classical data generating classical data, using some quantum algorithm in between, or it could be using quantum data using some classical computing to generate some other classical data. There's basically all combination between using some bits of quantum computing and some bits of classical computing, or doing everything quantum, and all of that kind of is encapsulated in quantum machine learning. And so that's the really big thing. And then maybe something very specific to this device is something called boson sampling. And that's basically you send the photons into this interferometer, and then just the probability distribution which comes out of it, if you have some photons in a lot of modes, optical modes, that distribution is something you cannot predict or you cannot sample from on a classical device very efficiently. So that's something where there is a clear quantum advantage, proven, no doubt. And then the problem is what to do with it. And so far we don't have like that much of an idea of exactly what to do with it. But one thing we figured out to do is we can encode a graph. So any kind of a graph, and not the graph to plot something, but like the mathematical graph of point nodes and edges. You can encode that into a matrix and then encode that matrix into that unitary matrix. And so you can, for example, use that to find if two graphs are isomorphic to each other. And you can do that via this boson sampling technique, which is very unique to this one. So that doesn't, for example, doesn't use qubits. And then there's one other thing. What we did, for example, was in I think it was a combustion engine or something, modeling a crack of like in the material using differential equation, and then again you can encode that into some algorithm and solve that. So there's a lot of optimization problems you can solve using some quantum algorithms, and the ground structure is sometimes quite similar, but there's very, very different algorithms to that. And a lot of them are variational algorithms, but some are non-variational algorithms. I guess one other thing could be there's something called QUBO. It stands for quantum binary optimization or something. I probably missed one of the letters, but basically there if you have some optimization problem where you have binary variables for the different scenarios, then you can use that algorithm. And so, for example, in logistics, you could think about what is the optimal way of where to produce and where to ship your goods. Or in financial markets, you could model some portfolio optimization. So it's still super broad in what fields you can apply these algorithms, because they are on the ground level are quite fundamental, and it's kind of still, the question is still up there where we actually find the use case. And then maybe in some fields it's possible to do it, but a classical computer can do it much, much better. And in other fields it's possible to do and a classical computer cannot do it better. So where, in which fields or in all these algorithms then become useful is still an open question. But there's a lot of potential, at least.
And there you have it, some more fascinating insights from Samuel on the vibrant world of quantum computing and the myriad of opportunities it presents. And here is the Science Show with Dr. Dada on JAMBO Radio Scotland. And we're all about mixing the thrill of discovery with the joy of great music. And so that's just another way to say it's time for another music break. And let's enjoy this song by Tana Musica entitled Selenkejo. This tune is, I can tell you, a vibrant one, a lively one, just as vibrant and lively as the quantum particles that we've been talking about. So enjoy Selenkejo by Tana Musica, and we'll be right back.
Me a dey moto party, oh, but I don't know about you. If you hear the gbedu, you go bounce. You go start to the one to the dance. Me a bere mole ma jojo. I go vibe like a this, like a so. Cause this gbedu, it dey make me dey do. Oh yeah, selenke jo, selenke jojo, selenke jojo, selenke jojo, selenke jo majo, selenke jojo. Ewo won bon ṣe wo wa. Ewo won bon ṣe wo wa. Ewo won bon ṣe wo wa. I beg you no waste this gbedu, oh. I beg you no waste this gbedu. And you gats move your body too, oh. So just put on your dancing shoes and start to the bust to the moves, instead of to just the look at the dancing a 2x2. cause this do. It dey make me dey do. Oh yeah, selenge, selenge jojo, selenge, selenge jojo, selenge jojo, selenge, selenge jojo, selenge, selenge jojo, ma jojo, selenge, selenge jojo, jojo. Ẹ wò wọ́n bó ṣe ń wò wá. Ẹ wò wọ́n bó ṣe ń wò wá. Ẹ wò wọ́n bó ṣe ń wò wá.
And we're back right here on the Science Show with Dr. Dada on JAMBO Radio Scotland, broadcasting from the city of Glasgow. I hope you enjoyed Selenkejo by Tana Musica. I hope it lifted your spirits and rhythmically matched the excitement we feel about the future of technology and science, especially quantum technologies. Now, as we continue exploring the quantum computing landscape with Samuel Horsh, it's clear that we are, in fact, standing on the brink of a new era. This is an era where our fundamental principles or understanding of these fundamental principles can lead to revolutionary breakthroughs in technology, medicine, and beyond. Of course, this is an ongoing area of research. Now, a big thank you once again to IOP Scotland for their support, and a reminder to all science enthusiasts, you can catch every beat of our show live on jamboradio.co.uk. So if you visit that webpage, you'll be able to enjoy our show and, of course, replay your favorite moments from the Jambo Radio Scotland YouTube channel. Now, we encourage you to subscribe to this channel. Of course, your engagement is what keeps our scientific heart beating, so to speak. So that is much appreciated. And let's keep those questions coming through your comments and through your shares. And of course, we will be delving back into this talk by Samuel now. So let's enjoy the last part of it.
In our case, the exact design which I just showed you will not work for the fault-tolerant era. That's not going to work. But the overall structure will be able to hopefully go into this fault-tolerant era. So using the same kind of source, using the same kind of photonic chip, but the way of using it will be very, very different. So in our case, it would be to use the spin of the molecule, of the atoms in the quantum dot, which was the single photon source, and then use the photons only as a carrier to manipulate that spin. So it would be a shift from the qubits being in the actual photons to the qubits being in the spin of the quantum dot. And then there's other companies who don't even bother trying to build a NISQ device, and they're from now on already starting. We're just going to build a fault-tolerant device. So for them, of course, they don't have any problem of changing, but also means it will be quite a while until they have anything to show off, because it's still quite a long way. And then there are other things which it's just not sure if it will be able to scale big enough to become fault tolerant. So if you think about superconducting, for example, which what IBM is doing, that's something which right now scales the largest, but there is a bit doubt that it will keep scaling that way. Whereas, and that's why we're doing photons, because we believe that even though now we might not as scalable as IBM's quantum computer, but there is not this limit of going to the really big scale. Whereas with superconducting or also with ions, just the devices itself becomes super, super big, and it's not really clear how to reduce that, and there might be some limitations there. And yeah, so I guess maybe I didn't say that, but maybe it's interesting to know that quantum computer which I showed you, this one, it's everything together, like all of this packed up, and then if you would buy one, is roughly the size of a fridge, like a kitchen fridge, like still a big one, but yeah. And we actually sold one of them to a data center. So, I mean, I wouldn't recommend you buying one. It's pretty expensive and you cannot do much and right now. But for big companies, it might be interesting so that they can then explore it. Yeah. And then other ones could be the size of a whole room. So the first use case the first project I got given was a molecular docking problem. So if you have molecules in pharma research or chemical research, you want to find out how two molecules dock to each other in what perfect angle. And you can model that classically to some degree, and you can also just try it out in the lab, but both of that is not really scalable. And so there's the idea to build a quantum algorithms to find the perfect docking angle of two molecules, and maybe to then help in the, I guess, more chemical industry. So that would be one thing, one specific use case. And now I'm working on this, what I said, the quantum generating machine learning algorithms. So there's a challenge BMW and Airbus had proposed, where they want to take a day image of a road or an airfield and then convert it into a night image of that. So put that in the generator and then generate a new image, but which is kind of the night version of that, so that they can use these images to train their machine learning algorithms, which then allow driverless cars or landing without a pilot. And so that's another thing which we are trying to solve, for example. So maybe I can just say, like, kind of the experience what the people have who I work with. So for me, for example, I didn't really know much about quantum computing, and they still hired me. So definitely there's not that much experience you need, because it's still a very, very new field. There are some people who do masters in quantum computing, and that helps, of course. But in the end, you still have to learn a lot of new things, because you will not cover everything, especially photonics is a bit more niche. So even the people who did quantum computing masters had no idea about that. And so there's not one way of doing it. There's also a lot of people who come from computing who don't have any physics background. Then that brings other challenges or advantages. So there's no one thing of doing. A lot of people, if you want to go into really like the theory or into the experimental physics, like deep technical things, a PhD definitely helps. There's a lot of people working at Quandela who has PhDs. Like, I think more than half of all employees have PhDs. But it's also, again, it's not a requirement. I don't have a PhD, and I don't, yeah. And then you can also do PhDs in industry. So a lot of, like our company, but also other companies will hire you as a PhD student, and then you can do your PhD within one of these companies in collaboration with the university, for example. And yeah, I would say if you studied physics, you're already pretty good starting conditions, because as the main thing is just understanding the overall, like, basically be able to then learn all the details, and you don't have to know anything specific. And even if you don't remember all the basics, you can relearn them. So I would suggest, if you're interested in that, just apply to some things and see how it goes.
I'm sure you're taking the quantum information course probably had something to do with it as well.
Yeah.
Probably helped a little bit.
Yeah, I think absolutely. I think it definitely gave me the first, I guess, the idea. I didn't really know anything else about quantum computing before, so I'm not sure if I would have applied to quantum computing startups if I didn't have taken that course. And it also helped a little bit in the interview process, so I had something to talk about. But as I said, they didn't expect me to be an expert already. They were more looking for someone who is interested to learn more about it and get into the field. So there was no like, oh, you don't know about this specific algorithm, then you can't work here. No, that's not what it is. And the people we now hire is the same. Like, it's very varied what their expertise is, and not everyone has to study physics either. Most of our interns will be doing it during their master's years, so either just afterwards or during it. So we also have some people writing their master thesis with us. We now also have one intern who is writing their bachelor's thesis with us. So it can also work, but if you're in like your first year of undergrad, then it's I don't think we would have internships, because if you like the interns we have, they're proper working with us. It's not just like getting to know everything. It's like you have your own project, and then you do proper work which someone else would also do. And of course there may be bit less expectation of how fast you do it, but you still have to learn all the same things, and like So you need some basic background in what's quantum mechanics and stuff like that. But yeah, absolutely, you can do it anytime. And we don't. So the internships I mentioned, they will not be all visible on the on our website where we have our job postings. So if you want to do internship, you can just message us directly. And we don't have just one time in the year where we take interns. Generally in the summer we have more, but any time of the year it's possible. And also in all of the different areas, if it's experimental, theoretical, software, whatever you're interested in. Yeah.
I was wondering if you'd like to show us something on the cloud. Just
okay.
Give us an idea. Not necessarily run something, but just how it looks.
You can go on, if you go on Percival Quandela, then you find the documentation of our software, and there will also be a section on how to run something on the cloud, and you can make an account for free on the Quandela cloud, which if you just Google Quandela cloud, you'll find it, and you get some free credits just by making the account, and then you can upload some of your code in some on the cloud directly, and then run it. And if you would at some point run out of credits, then you can pay for more. But there's at least for trying it out, there should be enough for you to play around with it. And you don't really need the cloud directly if you want to learn how to use Percival and run stuff on the quantum computer, because Percival itself is just a Python library. You just install it on your local device, and you can do everything you can do on the cloud also with that. And actually you can do more with the in the simulation. So you can simulate all of it on your laptop, and then once you feel like, oh, this might be an interesting thing, then you can go onto the cloud and upload it. Yeah. And if you want to really give it a go, you can come to our hackathons, and there you will get some like intro workshop of how it's used. You don't have to know anything before about our software, and then you just that's I guess how you learn the fastest, if you go straight into the deep end.
No, that's great already. Thank you.
Yeah.
So what degree of freedom of the photons do you use primarily, just to clarify
the spatial degree? So you mentioned polarization before. That is something which is theoretically very much possible to use, but in our case we do not use that at all at the moment, and we only use the spatial degree of freedom in which mode the photon is. So a photon in, let's say we only have two modes, then the photon could be in either of the two modes, or in any superposition of the two modes. So that would be then the degrees of freedom we use for the photons. Yeah.
So by mode you mean path?
Yes. So
right?
yeah.
So on a chip,
mode,
you have
path, optical fiber, like each of these lines, where path is a better way. Yeah. We call it modes. That's why. Yeah.
Yes, they are modes.
Yeah.
They are modes.
But yeah, just spatial modes. So, and it's very important that these photons are indistinguishable. So all of these photons will be exactly the same in order for that to work. So that's another source of error from the source from the whole setup, that if two photons coming out and they're slightly different, then all of this wouldn't work. So we have to kind of filter that out. But the sources are actually quite good at that, so it's not a big problem. Yeah.
Great. All right. So I think we'll thank Samuel again and call it a day there.
Thank you very much.
Wow, that's a fantastic talk by Samuel Horsh. We really thank Samuel for visiting us here at the University of Glasgow. As we said, today it's a special edition of the show. The show is actually hosted on campus at the University of Glasgow, where Samuel did his talk. And as we draw the curtains on today's quantum exploration on the Science Show with Dr. Dada, I would like to extend a heartfelt thank you to each and every one of you for tuning in from across Glasgow, Edinburgh, and beyond. So as we say goodbye for now, we will leave you with our theme song, a tune that encapsulates the spirit behind the very idea of the show: discovery and innovation. And that's, of course, what drives us, isn't it? So here's Science by Tana Musica. And until next time, stay curious, stay inspired, And of course, stay tuned for more adventures in science right here on The Science Show with Dr. Dada on JAMBO Radio Scotland. Bye for now.
New on the radio, there's a science show where the pros help us learn and grow, keep us in the know. Tune in and follow us, come join us, we discuss. Let's unwind, challenge your mind. The Science Talk Show. We're live from Glasgow on JAMBO Radio. The Science Talk Show. We're live from Glasgow on JAMBO Radio. Bring you the latest news through the interviews we infuse, give you expert views, knowledge you can use. Atoms to galaxies, so many mysteries. All the way we learn and play. The Science Talk. We're live from Glasgow on JAMBO Radio. The Science Talk Show. We're live from Glasgow on JAMBO Radio. Talk about the stars up high, planets in the sky, rockets fly, how dinosaurs died, warping space and time. Study the universe, its secrets so vast. You discern, there's much to learn. The Science. We're live from Glasgow on JAMBO Radio. The Science Talk Show. We're live from Glasgow on JAMBO Radio.